Okay, so I've been using the word orbital a lot, and we started by talking about orbitals as our probability function, our probability distribution of where you find the electron close to the nucleus. Like we started with this spherical orbital, but now let's get a more technical definition of orbitals. So the location of an electron can be described with increasing precision. What does that mean? So electrons are sorted into shells based on their energy uh, and distance from the nucleus, which is related to the energy. And that is n. Remember, n is our principal quantum number, which tells us about the energy and size of the orbital. Okay? Within those shells, electrons are sorted into subshells. So that is our L. So there's like an n equals 1 shell, an n equals 2 shell, an n equals 3 shell. And then within those, we have our L equals 0, or for n equals 2, we have L equals 0 or 1. So there are options. So and when n equals 1, there aren't really options. But when n equals 2, we have the L equals 0 subshell or the L equals 1 subshell. So we have two options. And then we have more options when we go up to n. So we found the shell, and now in that shell, we've found an orbital. Or sorry, we've found a subshell. So we're getting a better definition of where the electron is in the atom. We're getting increasing precision. All right, so what about within subshells? Within subshells, electrons are sorted into orbitals. So, for example, if L equals 1, m sub L can be -1, 0, +1. So, or sorry, m sub L can be -1, 0, or +1. So those are the orbitals. This is a shell, the n equals 2. The subshell is L equals 1. And the orbital itself is m sub L equal to 1, or m sub L equal to 0, or m sub L equal to +1. Each of those is a different orbital, okay? So when we're talking about these orbitals, we're still talking about the probability of finding an electron in a certain location. Now we have it narrowed down to a specific orbital, not just a shell, not just a subshell, but the specific orbital in that subshell. So this picture down here is something called the radial probability distribution. So what that means is the probability of finding the electron at a certain distance from the nucleus. This is just a different version of drawing it than we had with the one that looked like this. So for this, we're looking at a 2s orbital. It's kind of hard to see, but at the bottom there it says 2s orbital. So n equals 2, L equals 0. So for a 2s orbital, the probability of finding the electron is bigger further away from the nucleus because we have more energy when we get to the n equals 2 shell than we had in the n equals 1 shell. So there's actually a smaller probability down here of it being closer to the nucleus. Because we gave it more energy, it's more likely to be farther from the nucleus. When we look at the 3s orbital, n equals 3, L equals 0, we get the same idea. So now we can be even further away. Here our maximum was about 3 picometers, I would say. So that's 10 to the -10th meters, I think. Oh, sorry, 10 to the -10th is something called an angstrom. That one you don't need to remember, but it's in between picometers and nanometers. So that looks like about 3 angstroms away from the nucleus. And this one, for the 3s orbital, the maximum is like 7 angstroms away from the nucleus. So now we can get further away because the 3s orbital has higher energy than the 2s orbital. We gave it more energy so it can get further away from the nucleus. So the probability of finding it is higher further away from the nucleus. Okay, that's all I wanted to show you with this probability distribution, these graphs. Here is another table for you guys. This table breaks down the principal quantum number, which is n, the L subshell, and the orbitals. So when n equals 1, once again, L can only be 0, which corresponds to an S subshell, so the 1s subshell. And then within that subshell, there's only one option for m sub L. It's m sub L equal to 0. So note, up here, it's not the actual m sub L values, it's the number of m sub L values. So the only m sub L value is m sub L equals 0. And that is the 1s orbital. So now we can call it an orbital and not just a subshell because we know the orientation, not just the shape and size. When we go down to like n equals 4, then we have a lot of options for L. So let's look at L equals 2. That's our d orbital. L equals 2 always corresponds to a d subshell. Sorry, I should say subshell, not orbital. They all kind of become interchangeable after a while, but this is the 4d subshell. The 4 comes from the n value, the d comes from the L value, and there are 5 options for m sub L. We can do m sub L equal to -2, -1, 0, +1, and +2. So that's 5 options. And these are the 5 options. There are 4d, all these 4d orbitals, there's 5 of them. The 4dxy orbital, the 4dxz orbital, the 4dyz orbital, and the 4dz squared orbital, which is that weird one, remember? Bloop. And the 4d x squared minus y squared orbital. So there's 5 of those in the 4d subshell. Okay, so this table will be really helpful for you to know the number of subshells, the number of orbitals in the subshell, which orbitals those are, etc., etc. All right, so let's look at a picture, a visual version of that. So we have our 1s orbital. This is drawing our radial distribution function on XYZ graph. So it's a spherical orbital, the 1s orbital. You're most likely to find the, or you're only going to find the electron in that shaded spherical region. We go up to the 2s orbital. That spherical region gets bigger because we can find the electron further away from the nucleus. And we also have the options of the 2p orbitals. So those have these dumbbell shape or figure 8 shapes. And the probability of finding the electron is 0 in any of the non-shaded regions. So you're only going to find the electron in these shaded regions when it's in the 2p subshell or one of the 2p orbitals. Then if we go bigger, we've got 3s. So that's, you got a further, you got a probability of finding the electron further away from the nucleus because it's got more energy. Still spherical if it's an S shell or subshell. Then we got the 3p's, the 3p's. And those are bigger than the 2p's, you can tell. This is sort of to scale, I guess. So then the spheres don't just get bigger as we go up to higher levels of n. All of the shapes get bigger. So the dumbbells get bigger too. So you're more likely, or you're likely to find the electron in a bigger region, but it's still a figure 8 shaped region. And then we also have the d orbitals. So these are these interesting shapes. Here's that 3DZ squared orbital, which I said looks kind of like a dumbbell with a donut around it. And then the others are just clovers. So these are available when n equals 3, L can equal 2, which is corresponding to the d subshells. And those have a even more interesting shape of where you might find the electron near the nucleus. And then down here we have a different way of representing the same thing. We have our n equals 1, L equals 0, n equals 2, L equals 0, we go here. N equals 2, L equals 1, we go there. N equals 3, whoop, and L equals 0, we go to the 3s. N equals 3, L equals 1, we go to the 3p. And then n equals 3, L equals 2, n equals 3, L equals 2, we go to the d orbitals. So if you go to n equals 4, you can go all the way to the f subshells, the f subshell or the f orbitals. There's 7 of those. So we keep adding 2 more each time we go up. So there was only 1 orbital for n equals 1. When we go to n equals 2, now there's 3 orbitals possible. When we go to n equals 3, there's 5 orbitals possible in the d subshell. So you also want to think about the total number. So I should have said that. So for when n equals 0, when n equals 1, sorry, we only have 1 orbital option. When n equals 2, we have 4 orbital options. 3 for when L equals 1 and 1 for L equals 0. When we go up to n equals 3, we have 5 options for L equals 2, still 3 options for L equals 1, and 1 option for L equals 0. So in total, we have 9 options. So 1, 4, 9. You don't need to remember this pattern, but you should remember how this organization is set up, okay? All right, so what are nodes? So we didn't talk about nodes yet, but let me go back to here. So look at this probability distribution. It goes to 0 in these random places, even though it doesn't increase steadily and then go back down. It has these weird zeros in the middle of the probability distribution. Those are nodes. The electron has a 0 probability of ever being in that region around the nucleus. The nodes represent regions of no electron density, 0 electron density. So for the 2s orbital that we had, it looked something like this. And the 3s orbital that we had that looked something like, oops, this. If those went to 0, let me draw my axis a little better. So those spots, this white node corresponds to this region where there is no electron density. There's 0 probability of an electron being there. And we have another one when we get up to, oh, I guess that one is there. Then we have another node when we get up to the 3s orbital. So now there are 2 circular regions around the nucleus where the electron has no probability of being, even though that's kind of unexpected. We also have nodes when we look at p orbitals and d orbitals. So those are called these planar nodes. So this is the nodal plane for the 2px orbital. It chops it like right in half. There's a 0 probability. If you look at it on this graph, maybe it's easier to see. Chops it right in half. There's a 0 probability of the electron being in that region. So we have nodes on our s orbitals and our p orbitals. There are nodes for the D and F orbitals too. Okay, so just remember that a node is a region of no electron density. There's 0 probability of an electron being there. All right, and now let's talk about orbital energies. So, like we talked about with the Bohr model, when an atom absorbs energy in the form of photons, we shoot light at it, or we shoot power through it using like an electrical outlet. The atom absorbs energy and the electron is excited to a higher energy level. It goes from a lower energy level to a higher energy level. When the electron drops back down, this one is emission. So it emits a photon instead. But let's talk about absorption for now. So when the electron goes to a higher energy level, then that means that, when the electron goes to a higher energy level, that means that the electron can get further away from the nucleus and enter the larger orbitals. So here we have an image of a 1s orbital. This is that probability distribution density kind of picture that I showed you before. So this is a 1s orbital because the probability distribution is like highly densely focused closest to the nucleus there. And when you use a photon, so you shoot light at this atom, and in particular, we use a 102.6 nanometer photon that's in the UV range. We shoot UV light at this atom, and the electron can suddenly go further away from the nucleus because it has more energy. So it can enter a larger orbital. So our orbital energy increases as n increases. So when n equals 1, that's our lowest energy possible. That's our ground state, if you remember our terminology. N equals 2 is a higher energy. N equals 3 is a higher energy than that. N equals 4 is a higher energy than that, and so on and so forth. The higher n gets, the higher the energy of the orbital, and the higher the energy of the electron in that orbital. So this is just a little summary of that. High energy electrons have a higher n value. Low energy electrons have a lower n value. High energy electrons are more likely to be found farther from the nucleus. I should say more likely to be farther from the nucleus, not that they are. And low energy electrons are more likely to be found closer to the nucleus. They have less energy, so they don't want to get as far away from the nucleus. And then high energy electrons are less stable. They're more likely to drop back down to the ground state. Low energy electrons, the closer it is, so if it's already at the ground state, it's really stable. It's not going to do anything. But if it's not at the ground state, it's going to drop back down to the ground state, making it less stable. Okay? Let's look at some more practice questions and then we'll be done. How many orbitals exist for n equals 2? So let's look at our options. N equals 2, what can L be? L can be 0 or L can be 1. What can M sub L be? M sub L, if L equals 0, has to be 0. What if L equals 1? If L equals 1, M sub L can be -1, 0, or +1. So I'm going to circle my groupings. So this is one grouping. L equals 1 and M sub L equals -1 is another grouping. L equals 1, M sub L equals 0 is a third grouping. And L equals 1, M sub L equals 1 is a fourth grouping. So if we write these out, When n equals 2, we've got a 2, so our orbital is defined by n equal 2, and L equals 0, that's an s, so there's a 2s orbital. When L equals 1, we've got the p orbital, so 2p, and then we have 2px, 2py, 2pz. Now note that we don't know that 2px corresponds to m sub L equal to -1. We don't know that. We have no idea, sadly, what the relationship is between the orbital and the m sub L value, just that there are 3 different versions. So these are our 4 orbital options. So our answer is there are 4 orbitals for n equals 2. Cool. Last one. Which orbital has the highest energy? So in the hydrogen atom, we're just going to focus on the hydrogen atom. I should have mentioned that the hydrogen atom, n equals 1, n equals 2, n equals 3, so on and so forth. These are all equal, but in other atoms, as we'll see in chapter 4, they aren't always equal. So n equals 1 could be here, and then this 2s orbital is here, but the 2p orbital could be even higher. It's not exactly the same like it is for the hydrogen atom. So the hydrogen atom, we're only worried about what the n value is. So we don't need to worry about the p's, the d's, the s's, the f's. For the hydrogen atom, it's just based on the principal quantum number n, which means that C, the 5s orbital, has the highest energy, even though s orbitals usually have lower energies, as we will see in chapter 4. All right, that's it, guys. I will see you in class tomorrow. Sorry for getting this video up so late.